the permutation and combination. So we can continue on with example 10 right here. It says you have 9 people standing in a line. 3 are adult females, 2 are adult males, and 4 are children. How many different ways can they be arranged if only their category is distinguished? So for here, we can state a theorem where if you have n things of which n are of one kind, n2 are a second kind, and n of k are kth kind, then the number of distinct permutation is, we can represent it as n factorial over n1 factorial times n2 factorial, then dot dot dot, times n of k factorial. So here we can say that the total amount of people we have is 9 people, followed by how many adult females? We have 3 factorial times 2 factorial, which is the 2 adult males, times the 4 children, 4 factorial. Now if we do some algebra, we get 9 times 8 times 7 times 6, 5, and then 4 factorial. We can see that this is 3 times 2 times 2 times 4 factorial. The 4 factorial gets crossed out, and if we plug this into our calculator, we get 1,260. Move on to example 11. This example is saying how many distinct permutations can be made from letters of the word Illinois. So here we can see that we have the word Illinois right here. Okay, the word Illinois. We can see that there's letters I, L, there is N, O, and then S. So here we can see that there is 1, 2, 3, 3 letters of the word I. For L there are 2. We can see there's 2. And then for N, O, S they are each 1 letter each. Now we can make the distinction from the last example. For using this theorem above, we can see that there are a total of 8 letters, so 8 factorial over. Very simple. Now we just distinguish each letter. So for the I, there's 3, so 3 factorial times the letter L, which is 2 factorial, then 1 factorial, 1 factorial, and 1 factorial. We can rewrite this as 8 times 7 times 6, 5, 4, and then 3 factorial. And then we can write this as 3 factorial times 2, because 2 factorial is just 2 times 1, and then 1 factorial is just 1, so we don't have to write that out. We can cross out the 3 factorials from the denominator and the numerator, and if we plug this into our calculator, we would get 3,360 distinct permutation from the word Illinois. Now we can move on to example 12. We have right here, it says, in how many ways can 5 starting positions on a basketball team be filled with 8 men who play on any of the positions? So this is another case of permutation where we have 5 starting positions right here, and there are 8 men who could play any of the positions. So this is 8 permute 5. This is basically the permutation formula, which is 8 factorial on the top, and then we have 8 minus 5 factorial, which if we do some algebra, we get 8 times 7 times 6 times 5 times 4 times 3 factorial, and on the denominator we have 8 minus 5, which is 3 factorial, and the 3 factorials get canceled out, which we are left with the answer of 6,720 different ways. Examples we have right here. We can start with example 13. Suppose you want to create a 4-letter code using letters from the alphabet with no repetition, where order does not matter. How many arrangements are possible? So here's the key word. It says where order does not matter. So now we are dealing with combination. So we moved on for permutation. Now we're moving on towards combination. So with this example, for an example 13, we have a 4-letter code and where the order does not matter combination, and there are 26 letters in the alphabet, so we can say that this is 26 choose 4, which is equal to the combination formula, which is 26 factorial over 4 factorial, and then we have 26 minus 4 factorial, that is equal to the numerator is 26 times 25 times 24, and then times, what was in there? It was 24, then we have 23, and then times 22 factorial. The denominator, we have 4 factorial, and then 26 minus 24 is 22 factorial. The 22 factorials get canceled out from the numerator and the denominator, and we're just left with what we have right here. And if we plug this into our calculator, we get 1,000 or 14,950 for our answer. Now we can move on to example 14, which says we want to select 3 movies from a collection of 10. How many ways can this be done? So this is another form of combination. So we have right here 3 movies. We want to select 3 movies in a collection of 10 right over here. Now we can see that this is 10 choose 3, which is 10 factorial in the numerator, and in the denominator we have 3 factorial times 10 minus 3 factorial. This is equal to 10 factorial over 3 factorial times 7 factorial, because 10 minus 3 is 7. We can simplify this by having 10 times 9 times 8 times 7 factorial. Now in the denominator, we have 3 factorial times 7 factorial. The 7 factorials get canceled out, then we're just left off with this. Now we can just plug this into our calculator. Well, actually, we can simplify this more, getting 10 times 9 times 8. The denominator is just 3 times 2 times 1. If we plug this into our calculator, we get 120. So these are 2 great examples for combination. And so now we can move on to example number 15, where we are talking about a poker hand. So it says a poker hand consists of 5 cards. How many ways can we, and for part 1 is saying, how many ways can we select 5 cards from the standard deck of 52 cards? So this is another form of combination where we have, let me get my pencil, 52 cards, choose 5, which is 52 factorial over 5 factorial times 52 minus 5 factorial. So here we can simplify this as 52 times 51 times 50 times 49 times 48, and then times 47 factorial. And in the denominator, we get 5 factorial times 47 factorial, because 42 minus 5 is 47, I believe. Yeah, that's right. The 47 factorials get canceled out, so this is just basically 52 times 51 times 50 times 49 times 48 over 5 times 4 times 3 times 2 times 1. We can plug this into our calculator, which results in a very large number, which is 2,598. That looks ugly. 598,960. Cool, now we can move on to the second part, where it's saying how many ways can you select 3 aces from a standard deck of 52 cards where the other 2 cards are not ace. So for the first part, we know that in a standard deck of cards there are 4 aces. So here we can say that when we select 3 aces from a standard 52 cards, we would get 4 choose 3, because here we have 4 aces and we're choosing 3 of those aces out of a 52 card. But that's not it. We got to multiply this by 48 choose 2. Now it's 48 because you took 4 cards from the 52 cards, and 52 minus 4 of the aces you took is 48. So that's why now your standard deck would be 48. And then the 2 right here is the other 2 cards that are not aces. So you gotta get rid of those. And keep in mind this is combination, so we gotta, no replacements. So now we can just multiply these two, which would be, for the first part, it is 4 factorial over 3 factorial times 4 minus 3 factorial. Multiply that by 48 factorial over 2 factorial over 48 minus 2 factorial. Now after simplifying these two, we would get, on the numerator, we would just get 4 times 3 factorial over 3 factorial, because 4 minus 3 is 1, and 1 factorial is just 1. These cancel out, which just leaves us with 4 factorial. And on the right hand side, we give 48 times 47 times 46 factorial. And in the denominator, we're left with 2 factorial times 46 factorial, and the 46 factorials get canceled out. Then we would get, on the left side, 4 times 48 times 47 divided by 2. We can see that these two cross multiply, which leaves us with 2 times 48 times 47, and if we plug this all into a calculator, we would get the result of 4,512. Alrighty, so I cleared up some space, giving us more space for number 3 and 4. So we can continue on with this one. Here we have number 3 saying, how many ways can you select 4 hearts and 1 club from a standard deck of 52 cards? So here we have, we know that there are 13 cards of each type. So there's 13 hearts. So here we can see that in total there's 3 choose 4. 4 is the hearts, and 13 is the how many hearts there are in a standard deck of cards. We can multiply that by the 1 club. So same thing. The clubs, there are 13, choose 1. Now we can solve this by combination, giving us 13 factorial over 4 factorial times 13 minus 4 factorial times 13 factorial over 1 factorial times 13 minus 1 factorial. Now we can move on, simplifying it, giving us 13 times 12 times 11 times 10 times 9 factorial over 4 times 3 times 2 times 1. 13 minus 4 is 9 factorial. That's why we cancel out the 9 factorials. And on the right side, when we multiply the right side, we get 13 times 12 factorial. 1 factorial is just 1. 13 minus 1 is 12 factorial. The 12 factorials cancel out. And then on the left-hand side, we would get right here, 4 times 3 is 12. So the 12 cancel out right over here. And then the 2 cancels out with the 10, remaining with 5 right over here. And then we get right over here, which is 13 times 11 times 5, the 1 cancels out, times just 13. Now if we plug into our calculator, we would get 13, let me put in my calculator, 13 times 11 times 5. We would just get left off with just 9,295. Yeah, I believe so. Now we can move on to number 4. Number 4 is saying very somewhat similar to number 3. We'll find the probability of getting 4 hearts and 1 club from a hand of 5 cards. So same process. So here we have 13 choose 4 times 13 choose 1. But the only problem is that it's in a hand of 5 cards. So we divide this by our standard deck, which is 52, choose 5. Now we know what the numerator is because the numerator is the same answer for number 3, so we could just plug it in. The numerator is just 9,295 over, and we know the denominator back in number 1, which was 2,598,960. Now if we plug in this into our calculator, we would get, let me see, 9295 over 2.25. We would just get 0.00357. And yeah, that's how you do the combination.